Okay, so today we have three integrals that are connected quite nicely to each other. And this one over here, the one in blue, is an integral from the Berkeley Math Tournament 2020. And Black Pen Red Pen has made a video on it, and he solved it using Feynman integration. And I also used Feynman's technique to solve it in another video. After substitution to make it look better anyway, but you don't need any special techniques to solve this integral. You could just use integration by parts, and a result of these integrals that is quite commonly encountered in an introductory course on complex analysis, but I'm going to show you a much more elegant solution using only real techniques. And solving these two log-trig integrals just requires one property of the definite integral. That is, if you're integrating from 0 to some real number a, some real valued function f of x, then the results of integration are the same as if you're integrating from 0 to a, the same structure of the function f, but replacing x by a minus x. And I'm going to prove this technique as well to give you some concrete evidence that it works. And intuitively speaking, it means that whether you integrate from, whether you're adding up the areas under the curve from left to right or from right to left, it doesn't matter. The results are going to be same because you're adding up areas, right? So it's independent of the direction in which you're adding things. So basically we're trying to prove the equivalence of the two integrals under a transformation from x to a minus x. Now to actually prove that it works. So for that, if you're integrating from 0 to a, some function f of x with respect to x, now I'll leave it to you at the end of the proof to generalize this to integrals from a to b, where a and b are any two real numbers. So if you're integrating from 0 to a, some function f of x, and let's call this integral I, and let's perform a substitution where we let x equal a minus some other variable t, which of course implies that t equals a minus x, and as far as the limits of integration are concerned, well, as x approaches 0, t should approach a, and as x approaches a, t should approach 0. So your limits of integration are now kind of weird looking. Your integral I is now the integral from a to 0 of f of a minus t, and the differential element according to this equation, which implies that dx equals negative dt, so you have dt and a negative sign out here. So if I switch up the limits of integration, then I'll get another negative sign that cancels out the first one, so we have a positive sign outside. And so our integral, now I was the integral from 0 to a of f of x with respect to x, and this is equal to the integral from 0 to a of f of a minus t with respect to t. Now x, t, u, v, w, x, y, z, these are all just dummy variables. They don't alter the results of integration because you can just change the name of the variable without altering structure, right? So let's rename the dummy variable here as x. And this proves the equation I wrote out at the beginning of this proof. Okay, so now that we have our evidence that, yeah, the technique is going to work, we'll start by the first integral I wrote out, the integral from 0 to pi by 2 of the natural log of the sine of x. And I'm going to perform a transformation, which is commonly called a phase shift in the case of trig functions. Our upper limit of integration is pi by 2. So going from x to pi by 2 minus x, we find that I should be equal to the integral from 0 to pi by 2 of the natural log of sine of, now all you have to do is replace x by pi by 2 minus x. And we know what sine of pi by 2 minus x is, right? We know that this is the cosine of x. So we now have the natural log of the cosine of x that we're integrating from 0 to pi by 2. And this is actually the second log-trig integral that I wrote out. So we know that I, which was equal to the integral from 0 to pi by 2 of the natural log of sine of x with respect to x. And we know this is also equal to the natural log, the integral from 0 to pi by 2 of the natural log of the cosine of x. So these are both i's, and if you add them up, you'll get 2i, and the reason for adding them up is that you can make use of a very useful property of the natural logarithm. So the natural log of the cosine of x plus the natural log of the sine of x. Now, because of the natural logarithm, we can replace these two individual logarithms that are being added up by a single logarithm of the product of their arguments. So we have cosine of x times sine of x inside and 2i on the left-hand side. So if we divide by 2, that will get rid of the extra factor here. Now here we have the cosine of x times the sine of x. Now the product of the sine and the cosine is quite common in basic trigonometry. That is, if you multiply this by 2, and of course we have to divide by 2 as well, then what you have in the numerator is in fact the sine of 2x. So this implies that I equals 1/2 of the integral from 0 to pi by 2, natural log of 1 by 2 times the sine of 2x, integration with respect to x, of course. And what I can do here is I can separate this 1 by 2 again by using the properties of the natural logarithm. So I have 1 by 2 times the integral from 0 to pi by 2 of the natural log of 1/2 plus 1/2 times the integral from 0 to pi by 2 of the natural log of sine 2x, where we've made use of the fact that the natural log of a product equals the sum of their individual logarithms. So here is just a constant, right? The natural log of 1 by 2 is just a constant. So we have 1/2 times the natural log of 1 by 2 times pi by 2, right? So here's pi by 2, which I can just write up front as pi by 4, plus 1/2 of this integral that looks quite familiar to what we started with. And I'm going to perform a change of variable here to make things more clear. So if we let 2x equal u, which implies that dx equals 1/2 of du, then what we have now is 1/2 times 1/2 is 1/4. So 1/4 times the integral from 0 to pi, right? Because as x approaches pi by 2, u will approach twice that value. So the integral from 0 to pi of the natural log of the sine of u with respect to u. And this is exactly the integral that we started all of this off with. The only difference is that here we're integrating from 0 to pi and not from 0 to pi by 2. So how does this alter our discussion? Now you can actually draw some very nice conclusions about this integral just by considering a graphical analysis. So I'm going to consider the graph of the function y equals sine of x between 0 and pi. So we all know that this is what the graph looks like, correct? And we see this graph has a symmetry about the line x equals pi by 2, right? So by the symmetry, we mean that any area under the curve to the left of the line equals the area under the curve to the right. And we know that the function y equals natural log of x, the natural log of x is a 1-to-1 function, correct? So if we're considering the natural log of the sine of x, and in the case of this graph, the sine of x is actually on the vertical axis. So we see that equal values of the sine of x will give you equal values of the natural log of the sine of x, obviously. So by using these properties, number one, the symmetry of the sine curve about the line x equals pi by 2 and the one-to-one nature of the natural log of x, we can conclude that instead of integrating from 0 to pi by 2, 0 to pi, we could just integrate from 0 to pi by 2 and double the result. All of this is really cool because the integral from 0 to pi by 2 of the natural log of the sine of x is just the integral I that you started with. So writing this down here, we have I equal to pi by 4 times the natural log of 1 by 2, and added to it is 1/2, right? 1 by 2 times I. So if you transfer this to the left-hand side, you have I minus I by 2, which of course is 1/2 of I. So 1/2 of I equals pi by 4 times the natural log of 1 by 2. And you can cancel out these factors, and what you get is I equal to pi by 2 times the natural log of 1 by 2. Now that we know that the integral from 0 to pi by 2 of the natural log of sine x equals the integral from 0 to pi by 2 of the natural log of the cosine of x, and this equals pi by 2 times the natural log of 1 by 2, we are now in a position to tackle that integral from the Berkeley Math Tournament. That is the integral from 0 to pi by 2 of x divided by the tangent of x. Now what you can do is first up write this as the integral from 0 to pi by 2 of x times the reciprocal of the tangent function is the cotangent function. So this is what we're integrating. And by using integration by parts, we can integrate the cotangent function whose antiderivative is the natural log of the sine of x, and we're integrating this function. So x times the antiderivative of the cotangent of x, limits of integration are 0 and pi by 2, minus the integral from 0 to pi by 2, the derivative of x is 1. So just ignore that, and we have this antiderivative term, the natural log of sine of x. And we know what this integral works out to. And we can also evaluate this term on the left. Now the first term here evaluates to 0, and you can verify that using L'Hopital's rule. And the second integral here is something that we've evaluated above. It's pi by 2 times the natural log of 1 by 2. And there's a negative sign here as well. So this implies that I equals negative pi by 2 times the natural log of 1 by 2. And you can get rid of this negative sign using another property of the natural logarithm function. That is, all you have to do is reciprocate the argument and you get another negative sign that'll cancel out the first. So this Berkeley Math Tournament integral evaluates quite nicely to pi by 2 times the natural log of 2. So anyway, I hope you enjoyed the video. Be sure to like and subscribe. Thank you. See you next time.